Hello, and welcome to Design Considerations, discussions by engineers for engineers. My name is Ed Bray, and I will be your host for today's discussion on battery power. I am the Technical Sales and Applications Engineer with AEM Group located in Raleigh, North Carolina. Today I will be talking with Larry Schoettley. Larry is the Technology and Application Support Specialist for AEM Group. His experience includes more than 20 years of embedded design experience and high-power LED applications. Hi, Larry. Thank you for taking time today to help us understand more about battery power and what we need to keep in mind when approaching a design that will use battery power.
Thanks, Ed. It's a pleasure to get to share on this subject.
So when you're facing a design requiring battery power, what are some of the things that you think about?
One of the first choices in battery selection is to decide whether the end application requires a single-use battery, also known as a primary battery, or will the end application require a rechargeable battery, also known as a secondary battery. Single-use batteries usually have a slower rate of self-discharge rate than that of rechargeable batteries. This is something to consider for non-rechargeable applications that will set idle for an extended period of time before their first use of operation. If you're developing a battery-operated product, you must consider if the device needs extended power capabilities or extended energy capabilities. The operation time of a battery is dependent on the battery's capacity rating, which is designated in amp hours or milliamp hours. The amp hour parameter specifies the discharge current that the battery can supply over a specified period of time. If the end application needs to operate over long periods of time, then the battery needs to have the ability to provide that energy over that time frame. If the application requires a high current drain over a short duration of time, then the battery needs to have the ability to supply that burst of power during that short time interval. The designer needs to pay attention to the battery's energy content rating. You can determine the energy content of a battery by multiplying the battery's amp hour rating by the battery's voltage rating. The end result is the battery's energy rating in watts per hour. The energy of a battery is comparable to a bucket of water. If we have a 10-gallon bucket with 5 gallons of water and we open the faucet only partially, we'll get a certain amount of water to flow over a period of time before the bucket empties. If we want more capacity or energy without changing the faucet setting, we'll fill the bucket up to its full capacity of 10 gallons, which will extend the amount of water or energy available over a longer period of time. If more capacity or energy is required, we can always increase the size of the bucket. If we want more water flow or power over a short period of time, we simply open the faucet more to satisfy the output requirement. This is equivalent to reducing the value of the internal resistance of the battery in order to provide more current to the load, which results in more power output. Another important parameter to consider is battery voltage. What operating voltage does the end application require? The operating voltage is a parameter that will help identify the correct battery chemistry to use. Batteries that incorporate water-based electrolytes will usually have a voltage of 1.2 volts to 2 volts per cell. Lithium-based batteries, which implement organic electrolytes, can have voltage ratings higher than 3 volts, making them ideal for 3.3 volt applications. Don't forget about paying attention to the application's operating temperature range that the battery will operate in. Operating temps affect battery capacity, current drain rates, and charging characteristics. In rechargeable batteries, such as a lithium-ion, their maximum charging rate occurs between 20 degrees C and 45 degrees C. If the application's operating temp falls outside that window, reduced voltage and charging currents must be applied, which will result in longer charging times. Improper charging of lithium-ion batteries can lead to thermal runaway conditions, which can ultimately lead to a battery explosion. The entire operating scope of the end application must be evaluated in order to determine the correct battery chemistry to use, always designed with battery safety in mind. The end application's mechanical constraints will also determine the battery size and platform. Does the application require a coin cell, a cylindrical battery, or a battery pack? There are many options available when it comes to battery packages. And lastly, cost is the most important parameter to consider. How much will the implementation of batteries add to the cost of the end application?
Well, Larry, you've given us a number of valid points to consider. Thank you again for taking time to help us understand more about battery power and what we need to keep in mind when approaching a design that will use battery power. Thank you for listening. If you would like to be added to our mailing list, would like a copy of the transcript, or have topics that you would like to hear discussed, go to our website at aemgrp.com and submit under the Contact tab. Next time we will be discussing wireless design. Until that time, may your designs be safe, robust, and efficient. Goodbye for now.